All right, good afternoon, MEGN 301. Today we're going to be talking about FMECA, so failure modes, effects, and criticality analysis. And the general theme of what we're trying to answer here is how likely is a given failure to happen in our design. So what we want to be able to do is look at our whole design, take a look at what could possibly go wrong in there, and figure out how likely any of those given failure modes are so that we can prioritize our efforts well to make our designs more safe and more reliable. So here's an overview of what we'll be talking about in this video. So we'll differentiate what's the difference between FMEA and FMECA. We'll define the criticality number, which is the C part of FMCA, and discuss what that tells us about a failure mode, how we can use that information. Then we'll discuss failure rates and how to calculate them. We'll do some example failure rate calculations, and then we'll discuss with what we can do with the results of our calculations and how we can make our designs better, more safer, and more reliable. All right, so let's talk briefly about what's the difference between FMEA and FMECA. We talked a little bit about this in the previous video, but we'll just go over that again for your reference. So FMEA is failure modes and effects analysis. In FMEA, you're interested in identifying potential failures and the consequences of those failures. Okay. The big difference in FMECA's failure modes, effects, and criticality analysis is we want to identify which of those failures are likely to occur. And to do this, we define this extra term criticality. So criticality has a specific definition in risk and reliability engineering. It is a combination of severity and the likelihood of occurrence of a given failure. So failures that are more likely and/or have more severe consequences are more critical than failures that either don't have very severe consequences or aren't very likely to occur. The idea is if something's really severe or it's really likely to occur, we want to address those kind of failures earlier in our design process and try and get rid of those potential failure modes. All right. So this really leads us into what's the big picture of why are we doing this risk and reliability engineering analysis? Ultimately, what we want to make our system as safe and reliable as is reasonably possible with the resources and constraints of our problem. We only have so much time and so many resources that we can dedicate to mitigating potential failures and making our system more reliable. So we have to prioritize all the possible failures that could occur. Which of these failures should we prioritize? Well, there's two types of failures that we really don't want to have in a system. One is we don't want to have very severe failures. So if there's serious consequences to the failure mode, so could people die? Could people be seriously injured by this failure mode? Could we lose the whole system where it completely destroys our engineering system that we're working on? Things like that we don't want to have happen, so we would want to prioritize getting rid of those potential failure modes. The other type of failure that we would want to get rid of are likely failures. So if these failures are almost sure to happen, or they'll happen frequently and be a big maintenance headache, we'd like to eliminate those as well to make our system more reliable. All right, the way we identify these different failure modes that we want to prioritize our attention to is with the criticality number. So this is a method for ranking failure modes in the order sort of priority that we should address them in. So higher numbers of criticality numbers are more severe or more likely or both to happen. And an important thing to note here is that the criticality number is not an objective measurement, right? So there's no units on the criticality number, and it's not possible to take criticality numbers from one risk and reliability engineering analysis and compare it to a completely different analysis. The reason for that is as you're going to see, there's a lot of subjective engineering judgment that goes into calculating the criticality number. So you can't take a criticality number that's calculated by one team working under one set of assumptions and then compare it to a team that was working under a different set of assumptions. You're going to get radically different numbers, and they're not going to be an apples-to-apples comparison at that point. Okay, so what your criticality number is useful for ranking the failure modes within your own analysis, right? Don't try and take it and compare it to a completely different analysis. But the way we calculate The failure mode criticality number is with this given formula here where we say Cm equals beta alpha lambda sub p times t. All right, so beta in this is our probability of a loss of system functionality, which we'll talk about. Alpha is what we call the failure mode ratio. Lambda p is our failure rate, so that's how likely a given failure is to occur. It's usually defined as a failures per million hours of operation or million cycles of operation. And then T is the duration of our operation. So like how long does the mission of our prototype last? Many cycles or how many hours of operation does it go through before we've considered it to have completed its purpose? So we're going to break these terms down individually and talk about how we'll calculate each one of them just so that you can see how to get the criticality number. All right, so beta, that's our probability of loss of system functionality. So this is related to the severity classification that you did in your FMEA analysis previously. And essentially what it is we take our severity of our failure and we translate it into a decimal value that represents our best judgment as to the probability of a mission loss or severe failure of our system if a given failure mode occurs. So this is one of these subjective numbers. We're not going to try and compare these between our analysis and then some other team's analysis, but there's in MilSpec's 1629A, it gives this table that gives you sort of a rough estimate of how you can estimate beta. So if you have a failure mode, and if that failure mode occurs, you're definitely going to have a severe failure and you're going to lose your prototype or somebody could possibly get hurt, then we'd say the beta is 1. There's a 100% probability that we have a severe failure that occurs if this given failure mode occurs. So say you're looking at your shredder and you're looking at the failure mode where the whole shaft of your shredder snaps in half and it can no longer run. You lose the prototype and potentially you could eject pieces of the shredder out of its housing and injure someone, right? If that shaft snaps, you definitely have a severe failure at that point, so you would say beta equals 1 for that failure mode. Okay, if your failure is somewhat less likely, maybe it's just probable that you get a severe failure out of that, you would generally put beta somewhere between 0.1 and 1 for that, just based off of your best judgment. If it's possible, but maybe not really likely that you would get a failure, then we'd probably say beta is somewhere between 0 and 0.1. And if you definitely know that this is not going to relate to a severe failure of the system, there's not going to be an effect of the functionality of the system overall, then beta is going to be equal to 0, right? Because it's not going to cause a severe failure. All right. Next up is alpha, which is our failure mode ratio. So this is only for components that have multiple different failure modes that can happen to them. So alpha is, again, going to range between 0 and 1, and it's our best estimate of what fraction of the total failures that part can happen, what fraction of those failures is going to be this current mode that we're analyzing. So this only applies to stuff that can fail in more than one way. Okay, so if your component only has one possible failure mode, alpha is equal to 1, you can move on in your analysis. If you have a component with multiple failure modes, then all the alpha values for that part should sum to 1. Now, no, this is different than saying that all the alphas for your whole prototype should sum to 1. That's definitely not the case. It's for a given component of your prototype, all the failure modes, alphas should sum to 1 for that one component, not the whole prototype itself. All right. Students always have a little bit of trouble estimating what alpha is going to be. So when you get to the part where you're actually calculating failure rates for given different failure modes, just know that you can actually use those failure rates to try and estimate what alpha is going to be also. All right, so if you can use this little formula here where alpha equals lambda p over lambda c. So for that, lambda p is going to be the failure rate for this particular failure mode, and we'll divide it by a lambda c, which would be the sum of all the failure rates for all failure modes for this component. That can be a good way to estimate what alpha is for this particular failure mode. All right. Next up is lambda p, the failure rate, right? So for a particular failure mode. So the failure rate is typically defined in terms of a failures per million cycles or million hours of operation. If that number is higher, it means that a failure is more likely to occur because in a given period of time, you're going to have more failures. All right, there's a ton of factors that can go into affecting a failure rate. So it's like your operating conditions. Is your part hot while it's operating, or is it properly cooled? What quality was the part to begin with when you installed it? There's tons and tons of different factors, as you'll see when we get into the references here, that can all affect the failure rate. How do we actually estimate this failure rate? I'm just going to warn you, this is the hard part of the FMECA analysis. This is where you're going to be spending most of your time, is tracking down your components and figuring out how to estimate the failure rate for given failure modes of your component in your prototype here. All right, so let's talk about how we calculate this lambda p value. And typically what happens is we'll be using a failure rate model. So the way a failure rate model works is it has a base failure rate, and it's multiplied by a whole bunch of different multiplying factors that take into account different things. Things like the environment, the design safety factor, temperature, basically anything you could possibly think of that would have an impact on the reliability of a given component goes into one of these models here. All right, so the general model is going to look like lambda p equals lambda b times a whole bunch of different constants. And then what we have to do is we have to go in, we have to find an appropriate reference that will give us values for the constants and the base failure rate so that we can calculate what lambda p is. Just to relieve you a little bit, for any given component, usually a lot of these multiplying factors end up coming out to 1 because they're either not relevant or our conditions are such that it's mild and it doesn't have a significant effect on the reliability of the part. So we just go ahead and assume that those constants are 1 if they're not relative. Where do we get all this information? It takes a lot of testing of components to failure to calculate what these numbers are being and get a good estimate of how we make a failure rate model. It's really expensive and time consuming to do this research, but fortunately for us, a lot of the data have been compiled into handbooks for our reference. So again, the military is very interested in this sort of research because they want to know how reliable their hardware is. So they've spent a lot of resources to come up with really good data sets, and some of those are publicly available, which we'll be using for this project. All right, the two resources that you're probably going to go to most often for this would be the Handbook of Reliability Prediction Procedures for Mechanical Equipment. That's from the Naval Surface Warfare Center. And then that's a great reference for anything sort of mechanical, gears, belts, seals, shafts, all that kind of stuff. There's tons of great references in that handbook. If you're looking to see how reliable a piece of electronic equipment is, then you'll probably turn to Mill Handbook 217F, which is another military set of data that they've compiled. So any of your transistors, relays, resistors, circuit boards, anything like that you want to know how reliable it's going to be, that's where you're going to find it, is in Handbook 217F. All right. I've linked both of these resources in the PowerPoint slides, which you should be able to download from Canvas. You can go and grab the links from there. You can also just Google these resources. They're out on the internet, freely available, and just download a PDF so that you can have them for your reference when you're doing your calculation. All right. So I think the best way to understand how to do these failure rate calculations is just to jump in and do some examples. Because it's a lot of looking at charts, and it's a lot of flipping through references and looking up what terms mean and how to estimate each one of them. Generally, these resources are pretty good, and they give you the instructions on how to use them. So when in doubt, first thing is to read the reference and to just look up any terms that you're unsure of. There's usually a nomenclature section in each of the references. You can go back and figure out what the terms are, and they'll typically redirect you to a chart or a table or something where you can look up a certain value that you can plug into your equation. All right, and we're going to go ahead and do an example of that. So let's start off with a mechanical example. So this is going to come out of our first reference, and we'll be looking at an O-ring seal on a cap. So we've got a diagram over there on the right. Essentially, there's a threaded cap. Around the stem of that cap, there's an O-ring and a groove. And when we screw on the cap, it presses the O-ring to the sides, and it seals up our fluid so it doesn't leak out of the cap. We're going to say that our process fluid here that we're sealing up is clean water. It's 100 psi and 65 degrees Fahrenheit. This is a static seal, which means that once we screw down that cap, the seal's not moving. It's not like on a piston that's sliding back and forth, or there's no shaft that's spinning underneath it. Well, it has to seal pressure. The O-ring that we're using is a 1-inch ID, 16-inch thickness Buna-N rubber O-ring from McMaster. You can see the link in the presentation there if you want to go check out that O-ring for yourself. And then we're going to go ahead and say that the sealing surface was ground to a 45 microinch RMS surface finish, because the roughness of the surface has a big effect on how good the seal is with an O-ring. Okay. So if we go ahead and we flip through our mechanical handbooks, our Handbook of Reliability Prediction Procedures for Mechanical Equipment, if you come to section 3, you'll see that there's a lot of seals in there. And then if you go all the way into subsection 3.2.3, we'll find a component that looks a lot like what we're trying to do here. And it gives us a failure rate model. Okay, so it's again this format where we have our lambda p. That's what we want to know. Our failures per million hours for our specific system gives us a base failure rate to use in the calculation, and then it gives us a whole bunch of multiplying factors, which are all these C terms hanging off the end of our equation there. So for this one, I've gone ahead and written out what all of those are, and then in parentheses, I've given you the numeric value that I plugged in for this particular calculation. So you can go back and you can try and redo this calculation and check your work if you'd like to do that. And my failure rate was 1.95 failures per million hours of operation. Okay, I'm going to go through a couple of the more interesting terms here and talk about how I came up with those also. All right. So the first thing that I looked at, one of the important multiplying factors, is the pressure. So the more pressure we put behind an O-ring, the more likely it is that it's going to start to leak and the seal will fail. So for the handbook, when we go to look up the pressure multiplying factor and how to calculate it, it refers us to this figure in the handbook that says go to figure 3.10, and it will tell you how to calculate this particular multiplying factor. Okay, so what we do is we go on there and we put our pressure in. Our pressure is low; it's 100 psi. It's actually below the lower limit of that graph. Like the line doesn't actually go down that far. So if we look just below that graph, there's actually a little reference there. It says if your pressure is less than 1500 psi, then the multiplying factor for this term is just 0.25, right? So because our pressure is really low, we get a low multiplying factor. So we're actually less likely to have a failure because we have very little pressure in the system relative to some other systems. All right. Next up is the seal hardness multiplying factor. I picked this example out because it's a good example of sometimes we just don't have a great basis for estimating one of the multiplying factors. Right, so there's not a good reference on what the seal hardness actually is on McMaster for this particular O-ring. So we kind of have to guess and make a conservative estimate of what the multiplying factor for this should be. Ideally, we would have a measure of the hardness of the seal. We could just plug into this equation and figure out what the multiplying factor is. But in this case, we don't have it, so we just have to make a conservative estimate. All right, so essentially what this is doing is it's trying to consider if the O-ring is clamped with enough clamping force that it's going to make a good seal on the metal surfaces and prevent water from getting through there, right? So when you take an O-ring and you tighten down the cap that's sealing it there, it's going to squish the O-ring against the walls of our housing, and as the O-ring squishes, it kind of fills in all the little crevices on the surface that it's sealing up against, and it blocks water from getting through. If we don't have enough clamping force on there, like if the O-ring's really hard and we're not clamping it down hard, it's not going to fill in all the crevices and we're going to get a leaky seal. So that's what this multiplying factor is all about. In this case, we don't really have a great way of estimating that. We can see that the multiplying factor can go up quite high if we've got a very, very hard gasket. We can look on McMaster and see that Buna ends like not particularly hard compared to some other materials. Like we're not using like a steel gasket or anything like that. So we're just going to pick a conservative estimate. It looks like 1 is kind of towards the middle of the x-axis of this graph. So we'll just go ahead and estimate that this multiplying factor is 1, and it's not going to be a hugely significant factor for our calculation. We'll just roll with that because that's the best we can do in this situation. Okay? All right. Next up, we're going to look at the particle contamination factor. I picked this one out because it's a good example of a lot of times there's multiplying factors in there that are just not relevant to the problem that you're doing also. So this multiplying factor would come in if we had a hydraulic system. In a hydraulic system, there's a pump that's pressurizing your hydraulic oil that you use to do work with the system. And those pumps will slowly shed fine steel particles as they wear, which get into the hydraulic fluid, and then you have this fine, gritty steel material floating around in your hydraulic fluid, which can wear out the seals more quickly and reduce the reliability of your system. If we're just sealing clean water, it's not relevant to what we're doing, so this isn't going to have an effect on the reliability of our system. So if you run into a situation like this where you have a multiplying factor that's just not relevant at all, just use 1, right? Because that says that this does not affect the reliability of our system at all. It's not going to change the base failure rate because it's just a multiplying factor. So if we multiply something by 1, we get the same number back. So we're just going to go ahead and throw 1 into that so that we don't have to worry about that factor anymore. All right. So that's an example of how you can go through and do this sort of procedure for a mechanical system. Let's take a look at an electrical component this time. So we're going to be looking at the IRF 520 MOSFET. So this is the same MOSFET module that you used in MEGN 300 to turn on and off a light bulb if you're here doing that in person. If you did take the MEGN 300 in person, you'd probably notice that we burned up quite a few of these and let the smoke out of a lot of the MOSFETs because we were driving them pretty hard. So we're switching a 100 watt light bulb at 12 volts, which means our current that we're switching is 8.3 amps. So that's our application. We'd like to see how likely is this MOSFET to fail. Okay, so the way we're going to go about this is since we have an electrical component, we're going to be in Mill Handbook 217F this time. We're going to look through there until we find a transistor. So a MOSFET is a field effect transistor, and there's a page in there that says for FETs, which is a field effect transistor. And up at the top, this tells us it's an N channel or P channel silicon FET, which is what most MOSFETs are. So this is going to be a relevant page for us. All right, it gives us the failure rate model, which looks very similar. In this case, it's saying lambda P is lambda B times a bunch of pi terms. Why is it pi terms? Well, it's because Mill Handbook 217F uses pi instead of C for multiplying factors. It's the same exact thing as the other reference and what we've been talking about all along, but I'll go ahead and use Mill Handbook 217's F nomenclature just so it looks consistent with what you'll be seeing when you're using Mill Handbook 217F. But again, same thing as the C terms. All right, so it gives us our base failure rate model, gives us a temperature multiplying factor, an application factor, a quality factor that talks about the quality of the transistor itself, and the environment factor, and we multiply all those things together to get a failure rate. So let's go through those terms one by one, and we'll talk about how we picked values for all of them. Again, I've put my values in parentheses there, so you can go ahead and follow along with the calculation and check your work as you follow along there. Okay, so the first thing is the temperature multiplying factor. All right, so to determine the reliability of an electrical component, one of the biggest ways that electrical components fail is they get overheated and they burn themselves up. So we generally need to know the temperature that the component is operating at. So we can go ahead and we can find the junction temperature that's actually inside of the MOSFET. So there's actually a little guide in section 6.14 of Mill Handbook 217F that goes over how exactly to do this. It gives you a basic model to estimate what the temperature inside of your MOSFET is. So it gives us this equation where we have our junction temperature is equal to Tc plus this thermal resistance term times the power that we're dissipating inside of our component. So what we can do is we can follow along with their calculation there. We can give an estimated room temperature. We can talk about our thermal resistance of the case. So this goes into the package that your transistor is packaged into. In our case, the transistor is packaged in a TO220 case, which you could find on the data sheet for your transistor. And it gives us back in a table value where we can just plug in a number for that theta term. And then we can also figure out what the power being dissipated by our MOSFET is. So remember, P equals I squared R, so we know our switching current. We need to know what's the resistance of our MOSFET when it's turned on. So MOSFETs don't become perfectly conducting when they turn on. They have a little bit of resistance to them. And if you go into the data sheet for a given MOSFET, it's going to tell you what that is. So we were looking up the resistance between the drain and the sink. That's the resistance the current has to go through when we're switching it. All right, and if we do that, we find our junction temperature is 128 C, which is quite hot. All right, and if we go ahead and follow along with that, it's going to give us a multiplying factor of 5.4, so we're more likely to fail because we're running hot in this situation. Now, I want to point out one thing. If you go back to the data sheet on this particular transistor, you'll actually see that the junction temperature is above the absolute maximum rating of this transistor. And what you'll find when we go through and do our calculations, the failure rate is like surprisingly low that we calculate. And if you took the class, you notice that we burned up a lot of MOSFETs in that class, and it would seem that our failure rate is actually a lot higher than what this estimate is going to give us. And this is why. Okay, we're above the absolute maximum rating of the transistor, which means our failure rate is going to be very, very high. So just a word of warning, if you come across something like this and you're exceeding the stated rated maximums of a component, kind of our failure rate model is not set up to calculate that, and all bets are off, and you should just assume that failures are going to happen at that point. If you do find you're exceeding the maximum rating of a component, definitely want to replace that component with something more beefy that is going to stand up to your application better. But for the purposes of what we're doing here, I'm just going to continue on with the calculation. I want to make a note there and give you a word of warning about paying attention to the maximum ratings of components. Okay. Next up is our application factor. So this is how hard we're working the transistor. We're switching a 100 watt load. So if we just look in that table that's outlined in red there, it tells us that our multiplying factor is 8 given the load that we're switching. Okay. Next up is the quality factor. So this is how good of a transistor you started off with. So there are different manufacturing standards for different electronic components that deal with quality control, and you can talk about how well those components were actually made. So obviously a well-made component will probably last longer than a poorly made or sort of cut rate component will. So the way to figure this out is you check your data sheet for your specific component. If it's labeled, if it's manufactured to a certain standard, it'll be labeled. It'll tell you. So you would look at the JANTAXV and various other standards. Those are all quality standards that the military has laid out. Most consumer-grade electronics are not made to those, so if you don't see anything at all, you'll select either the lower or the plastic rating there, and you'll notice the multiplying factor is a lot higher for those, meaning that they're more likely to fail. Okay, next up is your environment factor. All right, so where the component is used makes a big difference in how long it's going to last. So if we have a component, electronic component, and we're just using it in the bench in an air-conditioned lab, it's probably going to last longer than one that's stuck in a metal shed in the middle of the Mojave Desert or something like that, where it's really, really hot all the time. So Mill Handbook 217F gives you a whole table of different multiplying factors for different types of environments that you could conceivably using this. So these start off as GB is the most benign environment, so it's ground-based benign, so like on a lab bench or something like that, where it's not getting jostled around, there's not a bunch of vibrations, the ambient temperature is okay, there's not a bunch of radiation or anything like that that we're exposing this to. And the most severe classification that it goes up to is actually cannon launch, CL, which would be if you stuffed your electronics inside of a battleship shell and shot it out of a battleship. Is a very severe environment because there's extremely high G forces acting on your components. Okay, there's descriptions of each of these different environmental conditions in section 3.4.3 in Mill Handbook 217F. So you can check those out and read what those descriptions are. All right. So once you kind of go through this, that's how we'll calculate our failure rate models. What you want to do is go through the FMECA worksheet. All right. So from your FMEA, identify your 5 most severe failure modes, right? Or basically failure modes that you think will be common or be interesting to analyze somehow. Do some like real good ones that you have some data for. You can have a good failure rate model and really calculate a nice criticality number for. Okay. Normally you would be as thorough as possible, where you would go through every possible failure mode for your system and calculate criticality numbers for all of them if you want to do a really thorough risk and reliability engineering analysis. Mill Handbook's 217F actually contains notes that reminds you that you should include soldered joints and printed circuit boards for any system that you're analyzing, because they can actually be a significant source of failures. If you have a well-engineered system that's pretty reliable, sometimes those are significant failures that you need to account for, right? And then you can go through and fill out this worksheet, right? So again, for this class, we're just doing the top 5 failures for a real thing. You would be doing every single possible failure mode that you can come up with for your system. So columns A through F of the worksheet are actually just straight off your FMEA worksheet. So you can just copy and paste those straight over from your previous work. Then you're going to fill in beta, alpha, and lambda P for each failure mode and calculate the criticality number for each of those failure modes. Then you want to sum up the criticality numbers for each component that has more than one failure mode. And we want you to answer the question, which of the components have the highest criticality numbers? So which ones are most likely to fail and have severe failures as a result of those? So the higher the criticality number is, the higher your priority on that component is to address that. So let's talk about how do we go about actually addressing and mitigating these failure modes. So there's a couple of things that we can do when we do this sort of analysis. We find a critical failure that we want to take care of. One is we can change our design, right? We can swap out components that have greater maximum ratings. Generally, this would look like going to bigger bearings that can handle higher loads, making shafts bigger diameter, beefing up frames, using bigger belts, higher rated electronics, something like that, so that we can handle a higher load. But you can do other things also, like we can change the procedure that users follow to interact with our machine. So one thing that we commonly do is we have a maintenance schedule. So if we know kind of what our failure rate is, we can also estimate how long it's going to be till a certain component fails, right? And we can replace that component before it fails. So that's a great way to mitigate these potential failure modes. We create a maintenance schedule and we just make sure that we replace components before they fail. Right. The other thing that we can do is we can modify the standard operating procedure that users use to interact with our system. So we can write the standard operating procedure in such a way that we don't ever put our system in a situation where we can have a really critical failure. We make sure that we don't load up our motor so much that we could potentially snap a shaft or bend the frame or something like that. So just realize that there's lots of different ways that we can mitigate these failures, and it doesn't necessarily have to be just replacing parts and overbuilding the whole system. So be creative in thinking of how we can mitigate those failures, and just make sure that you're thorough and you check out all of those top 5 failure modes and calculate a good criticality number. As always, if you have any questions, stop by class. We'd be happy to point you to different references and talk through how we can estimate those multiplying factors to get a good failure rate model. And we look forward to seeing what you come up with in class.